Hello everyone, thank you so much for attending this talk. I am Said Mohammed Jawad Talebi. I conducted this research with collaboration of researchers from UC Irvine and Microsoft. Today I'm going to talk about MegaMind, a platform for security and privacy extensions for voice assistants. First, let's see what the problem is. Nowadays, we can find voice assistants everywhere. Several brands offer voice assistants and they are available on a variety of devices. Voice assistants usually consist of two main components, a client device and a cloud service. Client device is usually a simple piece of hardware which has a microphone that always waits to hear its wake word, such as Alexa. It also provides the HTTPS client to connect to the cloud service and a speaker to play the responses to the user. All the magic then happens in the cloud service. It performs the speech recognition, it processes the user's requests, handles them, and provides audio responses. In addition, most of the voice assistant cloud services might forward some of users' requests to third-party services to get handled. Given the similarity of all voice assistants ecosystem, without losing generality in this work, we focus on Amazon's Alexa. In Alexa's ecosystem, the cloud service provider is named Alexa Voice Service or AVS. The client devices are Amazon Echo devices or any other third-party device which integrated AVS Device SDK, which is the open source platform to communicate with the AVS. And the third-party services are named skills. Now, let's review some of the existing security and privacy problems with the voice assistants. As client devices are always listening for their wake word, they might mishear a word and accidentally get triggered. For example, a user might ask her friend for Alex ID number, but the Echo device can confuse the words Alex ID with Alexa and forward the following conversation to the AVS and violate users' privacy. In addition, Alexa's parental control is very limited. It does not allow parents to enforce their customizable filters on what their children can do with and hear from their Alexa-enabled devices. The problem seems worse when we know there are so many third-party skills for Alexa, which all of them are enabled by default for all the devices. An important limitation of voice assistants, for example, Alexa, is that you need to always trust their cloud service, because it's the one who always transcribes and distributes users' commands. Even if you're using a sensitive and more trusted service, such as your bank or your hospital. So let's see what we can do to solve this problem. Users have no control over how their voice gets processed in the cloud services. In contrast, users own their client device hardware, especially when they're using open source implementations of device SDKs. They even have control over the software that runs on their devices. In MegaMind's threat model, we completely trust the client device. So our solution to users' lack of trust to the cloud components of voice assistant is to run some codes locally on the client's device to enhance security and privacy. To achieve the mentioned goal, we provide MegaMind. MegaMind is a platform which allows security and privacy extensions to run on the client device. These extensions process user commands before leaving the client device and voice assistance responses before they get played for the user. Now, let's see a few examples of extensions that MegaMind enables. For example, a redactor extension can protect users' privacy by replacing user's name with a random name. Or as another example, using MegaMind's extensions, users can communicate with a trusted third-party skill securely without even AVS accessing the communication. I will later how MegaMind achieves this goal without using any communication channel other than the AVS itself. Moreover, to protect your privacy, sometimes you don't even want AVS to know which skill you are using. To achieve this purpose, you can use a mixer extension that MegaMind enables, and the mixer skill, which mixes different users' queries and randomly submits them to one of its several Echo devices. MegaMind enables many other extensions as well. For example, you might want to deny access to a list of a skill. You can disable a device in certain hours of a day. You can apply customizable parental control on the Alexa devices which are installed in your children's room and many other extensions. Now I'm going to talk about the design of our system. MegaMind has several components. Let's see these components in action with a simple example. Alexa device SDK wake word detection get triggered when a user says the word Alexa. Normally, this results in transferring the user's utterance in audio format to the AVS. However, in our solution, MegaMind captures the wake word detection signal and starts a local speech-to-text engine. The speech-to-text engine then transcribes the user's command and passes it to the MegaMind processing unit. In the processing unit, extensions process the user's command to apply the additional privacy and security protections. Then it passes the processed command to the Alexa device SDK. Please note that securely processing human language by multiple untrusted extensions is a very challenging task. I will later talk about these challenges and how MegaMind overcomes them. Alexa device SDK normally records users' audio and pass it to the AVS. We modified the device SDK to receive text inputs instead and also pass text queries to the AVS. After AVS handles the user request, the responses get processed the same way as the request, but this time only in the opposite direction. Now, let's see what are the challenges that I mentioned, challenges of processing phrases by extensions. First, we assume that any third party can provide these extensions, so we cannot let extensions do whatever they want. And second, there might be cases that the single phrase needs to be processed by several extensions, so we need to make sure that different extensions do not interfere with each other. Providing these two security guarantees is a very challenging task. It involves a lot of components, and going through all of them involves discussing a lot of technical details. In next slides, I will only discuss a few interesting aspects of MegaMind security guarantees. For example, for complete description and analysis of each guarantee, please take a look at our paper. First, let's talk about our permission enforcement. MegaMind provides a permission model in which extensions, access permission, and modification permissions are in balance. Extensions that can access a broad variety of phrases do not have that much freedom in changing the phrases, and extensions that want to arbitrarily change the phrases can only access a very specific type of phrases. To achieve this balance, we defined three extensions types. First type is extensions which are companion of a specific third-party skill. These extensions are developed by the developers of that skill to enhance the security or functionality of that skill. Companion extensions have limited access permission and can only access the conversations between the user and that companion skill, but they have a very powerful modification permission and can arbitrarily modify all the phrases in the conversation. Another extension type is sanitizers. Sanitizers can modify words in the user request or voice assistant responses. However, they do not have full access to all conversations. They need to clearly specify beforehand a list of keywords or keyword categories that they are interested in. They only can access phrases including those words, and they can only modify those words in other phrases. Finally, we have discarders. They have broader access permission, but they only can drop a phrase or end the conversation. As I mentioned before, another important challenge is how we can process a phrase by multiple extensions. Since some extensions, such as secure conversation extension, need to be able to arbitrarily change the phrase, it's impossible to reconcile the output of multiple parallel extensions. As a result, our solution is to execute extensions one by one in series, in a way that one extension first processes the phrase and the next extension then processes the output of the previous one. But obviously, the order of extensions execution matters. For example, if a companion extension already has encrypted a request, the next extension cannot do its job effectively. In our paper, we introduced two ways extensions can interfere with each other. First of them is under protection, which means undoing the protecting act of the previous extension. For example, if a redactor extension redacts the word, but next extension adds the word back to the phrase, or overprotection, which means that causing next extensions to apply an unnecessary protecting act. For instance, let's assume that we have a discarder extension which blocks phrases that include a forbidden word. If a previous extension adds that forbidden word to the phrase, it will cause overprotection. In our paper, we carefully investigated all possible ways that extensions can interfere with each other and cause underprotection and overprotection. We showed that there exists a specific ordering, that if we execute extensions with that order, they can all fulfill their goals without interfering with each other. Now I'm going to talk about two cool extensions MegaMind enables. For example, here we can see the description of a parental control extension. This discarded extension will end the conversation if any of the mentioned rules get violated. We developed an expressive and easy to review descriptive language that extensions can use to describe their rules. Please refer to our paper for more information on the descriptive language we developed. In addition, to further facilitate development of extensions, MegaMind provides several natural language processing helper functions. For example, functions to find synonym of a given word, or find phone numbers in sentences, or find profanity, and many other helper functions. In this example, I'm going to show you how a user can securely communicate to her bank skill using a MegaMind-enabled device. She first tries to open the bank skill saying, "Open Great Bank." At this time, MegaMind detects that a user wants to talk with a skill which has a companion extension, so MegaMind triggers that companion extension. The bank extension then generates a symmetric key to encrypt the messages of the following conversation. As the bank extension knows the public key of the bank skill, it encrypts the session key with that public key. The bank skill then responds with an unencrypted greeting message and asks the user if she wants to establish a secure channel. If the user answers yes, the bank companion extension replaces this message as shown in the slide, and instead of sending yes, it sends the encrypted key to the bank skill. The bank decrypts the session key with its private key, and now both extension and the skill have the session key, and they can securely communicate. As a result, the bank extension will replace all the following messages with the encrypted message. Now let's see how is the performance of MegaMind. We implemented MegaMind in 3 different platforms, and as you can see, it achieves low conversation latency for laptop implementation and even for a cheap and weak device like Raspberry Pi 4. I will later discuss why MegaMind suffers from higher latency on Raspberry Pi 3. To more accurately measure the MegaMind's latency overhead, we also measure and report the latency caused by each component, such as AVS device SDK, speech-to-text, text-to-speech, using NLP helper functions to evaluate which extensions should be used on phrases and the execution of the extensions themselves. We separately report the latency breakdown for 5 different extensions. This latency breakdown figure shows some interesting intuitions. For example, we can see that most of the latency for secure conversation extension comes from processing users' first request. I previously mentioned that the public key encryption happens on the first request. Or in this figure, we can see that evaluating NLP helper functions on Raspberry Pi 4 is way more time consuming than the laptop. It suggests that in future, we can improve the latency on this device by optimizing the NLP helper function based on its hardware constraints. Or we finally can see that the most of undesirable higher latency on Raspberry Pi 3 is come from the local speech-to-text detection. This suggests that for devices with very weak hardware, we might need to offload the speech-to-text detection to an edge device. We also measured the effectiveness of several MegaMind extensions to achieve their goals. MegaMind uses an open source speech-to-text engine which is trained for general speech, not for voice assistant usage. As a result, in order to separate the accuracy of MegaMind extensions from the accuracy of the speech-to-text, we once performed our effectiveness test normally using voice commands, and another time we directly submit the commands in text format. For example, we can see that MegaMind's privacy redactor extension could redact users' private information such as first and last name, contact information, and ID numbers with a high accuracy. In another example, we can see that MegaMind's Parental control extension finds and blocks all the bad words in the hundreds of jokes we ask it to play, and it achieves high accuracy in preventing purchases. In summary, MegaMind is an extensibility system for enhancing the security of voice assistants. MegaMind supports novel extensions, it achieves low latency, and it's highly effective to reach a variety of security and privacy goals. Thank you so much for your attention. If you have any further questions, please do not hesitate to contact me on my email. MegaMind is open source and available at the following link. We also have a video demo of MegaMind available at the same link. Thank you so much.